Good morning and good afternoon, everybody. I'm Gianpiero Cossarini. I'm from the National Institute of Oceanography and Applied Geophysics in Italy. And I'm a biogeochemical modeler, and I work for the Mediterranean component of the European Copernicus Marine System. And during this talk, I would like to show our works on the introduction of the assimilation of Biogeochemical Argo in the Mediterranean Sea operational system. I will briefly introduce the Mediterranean Sea and the biogeochemical component of the Copernicus Marine Service. And I will talk about the data assimilation we have in the model and the introduction of the biogeochemical Argo data. And I will show you some aspects we worked on for the optimization of a multi-stream data assimilation, and then I will conclude with some points. The European Copernicus Marine Service provides model results for the white, blue, and green oceans, for the global ocean, and for 6 regional European seas. The Mediterranean Sea, the red box on the top left of this slide, is one of the regional seas, and it started the operational service in 2012, in pre-operational mode in 2010, and since the beginning we recorded the quality of the forecast. In this case, the plot shows the time series of the root mean square error of the first day of forecast for the surface chlorophyll. The comparison was made with the ocean color data. And what is interesting to note is that this time series can detect the biggest change in the biogeochemical model system and the impact on the quality of the forecast. In this case, the first red arrow shows the introduction of the satellite ocean color assimilation in 2013, and in 2020 the second arrow shows the introduction of the biogeochemical data assimilation of biogeochemical Argo data. Of course, just 1 year ago, so we are not able to detect all the changes, but also because this time series regard the surface of the ocean. And the surface might not be enough to monitor in the marine ecosystem. In this case, for the Mediterranean, as shown in this nice three-dimensional picture of a summer day of chlorophyll. Important features are below the surface. In this case, the yellow strip is the deep chlorophyll maximum. They identify subsurface maximum of chlorophyll and, of course, the other biogeochemical component. And even if the Mediterranean Sea is a small semi-enclosed sea, the variability is quite high, as shown in the lower panel, with the deepening of the deep chlorophyll maximum depth and the decreasing in the intensity of the chlorophyll maximum at the DCM. For that reason, the biogeochemical Argo float can be a very important asset for the modeling activities in the Mediterranean Sea. And since the Mediterranean is a semi-enclosed basin, it is a very favorable condition for having a long history of float sampling. In this case, the two figures show the density of profiles for the period 2013 to 2021, and as you can see from the colors, most of the Mediterranean has been sampled, only the southern part and some marginal areas are not covered by the trajectory of the float, and the number of profiles is up to 10,000 for oxygen and 1/3 for nitrate. The object of my talk is to show how we implemented the assimilation of Biogeochemical Argo flows in the model of the Mediterranean Monitoring Forecast Center. The model system is composed by offline coupling of the physical system, which is based on the NEMO 3.6 ocean dynamics model, and the biogeochemical Flux model. And both the physical and the biogeochemical components, the blue and the green, have a data assimilation system, variational system. The physical system assimilates sea level anomaly and in situ profiles of temperature salinity, while for the biogeochemical green component, the variational system assimilate ocean color and, as I'm going to show, profiles of chlorophyll, nitrogen, and also oxygen. The system is forced by the NC and WF forcing, atmospheric forcing, and provide the Copernicus Marine Service with 14 days of analysis plus 10 days of forecasts that can be downloaded for free openly through the Marine Copernicus web portal. The core of the biogeochemical component is the BFM model. BFM is a medium complexity biogeochemical model based on plankton functional types formulation and describe the biogeochemical cycle of several chemical elements like carbon, phosphorus, nitrogen, silicon, oxygen. Here in this cartoon on your left is in the dashed black box is represented the part of the marine ecosystem that is simulated by the BFM model, and the flux is the interface with the sediment or the high trophic level are simulated by some closure terms. The BFM has also a carbon system dynamics that simulate the IC alkalinity dynamics and pH and the flux of CO2, the RC interface. The dynamics of the ecosystem simulated by the model can be improved by the integration of observations, and we do that using a variational data simulation scheme, and we use the observation from satellite, chlorophyll at surface, and the profile of oxygen, chlorophyll, and nitrate from Biogeochemical Argo. And the satellite assimilation was introduced in 2013, while the assimilation of Biogeochemical Argo flows was done in the Service Evolution project called Massimili. It was a collaborative works between OGS and the Laboratory of Oceanography of Villefranche, and was implemented in the operational system in April 2020. The variational data simulation scheme implemented in the Mediterranean model system is based on a minimization of a cost function which depends on a background error covariance and observation error covariance. The background error covariance matrix can be decomposed in several terms that account for the different dimensions of the error covariance. In this case, we have multivariate biogeochemical covariance that describe the errors among the biogeochemical variables, the VB term, then the VH horizontal covariance is controlled by a radius correlation length scale, and the vertical covariance is based on a multivariate empirical orthogonal function decomposition. We implemented, or I'm going to show you the results of a series of experiments that I meant to assess the different impacts of the different assimilation of different streams. In this case, on your bottom left, you have in black the reference simulation, which has no assimilation, and in the other colors indicate different combination of assimilated variables. And in particular, the red one, the last one, is the combined assimilation of satellite and biogeochemical Argo data. As a result of the biogeochemical Argo assimilation, the blue and the red lines, we observed an improvement of the simulation of the vertical dynamics of phytoplankton. I did the root mean square of the misfit, show a reduction of about 30–40% with respect to the black line, the reference simulation, mostly for the subsurface layer, and which are those most impacted by the assimilation of biogeochemical Argo. And what is interesting to see is that sometimes the red line, like in the Turanian, the second sub-area, show a worsening of the performance with respect to the black line because the impact of the assimilation of satellite. Same improvement in the vertical dynamics is observed also for nitrate. In this case, the assimilation of biogeochemical Argo seems to produce a larger positive impact in the western sub-area, the northwest Mediterranean and the Turanian area, and less intense improvement in the quality in the eastern area, the Ionian and the Levantine. And maybe this is because of the extension of the assimilation because of a number of profile available in the eastern part. In order to assess the spatial extension of the data assimilation, we computed an index based on the difference between the assimilated and the reference run. The index is integrated over the first 200 meters, and the results, which are reported in the two maps, are shown for two different seasons, the winter and summer. The yellow color indicates higher impact. If we go to the winter map, is mostly yellow colored, and this indicates that the data assimilation persistently changed the whole basin, and mostly because of the satellite data is assimilated. And this can also be seen in the profiles in the right part of the slide that show how the corrections are homogeneous and starting from the surface till the mixer layer depth. The comparison between the orange line, which is the reference profiles, and the blue line, which is the profile for the assimilated run. In summer, however, the situation is opposite, and the impact is lower and mostly centered on the float trajectory, which is indicated by the red boxes in the map. And up to 25% of the Mediterranean is impacted by the assimilation, and the profile correction are mostly in the subsurface layer, where the float assimilation corrects the depth and the intensity of the deep chlorophyll maximum. In the case of nitrate assimilation, we observe lower impact, which is mostly due to the lower number of floats available. And even if the area affected by the assimilation is less than 10% of the Mediterranean surface, the persistence is high in the area affected by the assimilation, and this is because corrections are mostly below the nitric line, as shown in the right plots, and since biogeochemical dynamics are slower in the subsurface part for the nitrate, the persistency of the new information are retained in the system for a longer time. Considering the object of maximizing the impact of the Biogeochemical Argo network, but also taking into consideration that the number of floats cannot grow as much as one would like, especially for sensor like nitrate, a possible solution for increasing the spatial extent of the data assimilation is work on the horizontal covariance in the 3D BIO system. This can be done by changing the correlation radius length scale. The correlation radius was computed using a past model output and through a cross-correlation analysis, and it resulted of the order of 15 kilometers, that is the dimension of the mesoscale in the Mediterranean. We tested in 100% increase of this radius. Of course, the spatial impact increases as well. However, the error might increase because the floats are mainly local observations, and they can go in conflict with neighbor observation or spatial features observed in the satellite. Dealing with the real-time use of biogeochemical Argo data, another issue is the real-time quality of the data. The quality of the data in the last year is greatly improved, but still for variables like oxygen and nitrate, they cannot be used as they are, and so we implemented a quality check that based on saturation at surface for oxygen or comparison with the World Ocean Atlas or results from the neural network Canyon B method. And for all the variables, also a check with the model observation misfit helps the data simulation system not to introduce information that are disrupting the model dynamics. As a result of the internal OGS quality check, the number of real-time profiles ready to use in the operational data simulation might be lower than the total number of profiles. As can be seen from this plot, during the last year we observed that oxygen quality real-time data perhaps decreases in the last 8-10 weeks. And for nitrate, the lower panel, the trend of available floats further decreases, and with just 2-4 profiles per week, the impact of assimilating these variables is very low. Another potential issue in dealing with real-time multi-stream data is the potential inconsistency between the different types of data. In this case, in the plot on the left, it shows the comparison scatter plot of satellite and float surface chlorophyll. And as you can see, during summer month, the green cross, satellite has a higher value, while during winter, the blue crosses, the satellite has lower value than the float profile. We partially overcome this issue by implementing a sequence of separate assimilation events for the different data streams. And it is the model that through dynamical adjustment solves the inconsistency between the different data streams. We can also act on the observation error of the different data streams and the different variables in order to optimize the assimilation. The observation error should also include the representation error, which consider the different spatial and temporal scales observed and simulated. Here are two examples of different approaches. And for the chlorophyll of Biogeochemical Argo, we adopted a method that considers the consistency between the a posteriori observation and background error using a set of simulation with different observation error. In the case of nitrate, because of the availability of three independent datasets, we adopted the triple collocation method that used cross covariances among the different datasets. And just to conclude, the float assimilation is feasible also in biogeochemical operational models and can have a positive impact in changing the vertical dynamics of nutrients and phytoplankton. This is most evident in summer and oligotrophic area when the subsurface layer is decoupled from the surface. Biogeochemical float assimilation has mostly a local effect, and because of the number of observations, the area that is affected can be low. There are possible strategies in order to increase the impact of biogeochemical Argo network. And the other aspect of the data stream data assimilation has to be considered in order to optimize the multi-stream data assimilation benefit. And thank you for being here, and I would like also to thank all the OGS staff working on the Mediterranean Biogeochemical Forecast Center. You can follow us at the medef.inogs.it, and also the colleague from the Mediterranean Center for Climate Change and from the Hellenic Center of Marine Research. And also I would like to thank colleague from the Oceanographic Laboratory of Villefranche for working together on the Massimili project.